Okay, it's a little bit scuffed, but we'll just keep writing out some values just to be a little bit faster. Okay, so we have the situation where this wheel is being pushed, and then so the wheel is spinning, and it is revolving around point O, which is fixed. And so we're asked to find the angular momentum, but only for the z component. So we can use this equation where the angular momentum around the center of mass for the z direction equals the moment of inertia in the z direction, the angular velocity in the z direction, this will be k hat. And then so this IZZ c term is the integral of the x squared plus y squared dm. And then this will equal to the mass times the radius squared at the center of mass. And then so that equals 12.5 times the radius, which we calculated by this angle geometry, where if this angle is beta, which is given, this angle is 90 minus beta. And then so we can use trigonometry to find that the radius, my marker isn't working very well, but is 3.75 meters. So we square that, and then we multiply it by the mass. So 12.5 times 3.75 times 3.75. And that equals 175.78 kilograms times meter squared. And now we have to find this angular velocity in the z direction. And it's defined here that the z direction is through the center of the wheel. So that's my k hat. And then, okay, let's see. And then just for the purposes of notation, I'll say this unit vector is just some arbitrary like I hat. Okay, so first let's find the angular velocity of the ring about its center of mass c. Maybe I should use a different marker. Okay, and then so we have the angular, oh wow, that's good. Angular velocity of the ring about the center of mass in the k direction equals, so it revolves, it does one revolution, which is, okay, hold on. So if you do 2 pi r, b over 2 pi r, then you get the circumference of the total distance it revolves, and then you get the how many times this circumference is like kind of, I guess, repeated within this 2 pi b circumference. And then the 2 pi's cancel out, and then you multiply this by 2 pi over t for 1 revolution, and then you get, so this would all be in the I hat direction, but you want it, actually, sorry, this would be in the k hat direction. I wrote it wrong in my work. And this would be negative 1.64 radians per second in the k hat direction. And then I believe it's negative because if you're doing the right-hand rule, if you're pushing it this way, which the boy is doing, it's kind of hard to explain. Like, I guess if you imagine adding this force, then the wheel will turn this way, but the right-hand rule says that the k hat positive rotation is in the other direction, so we use a negative. And then now, I guess it's not a vector because it's just a k hat. Okay, so now we have the angular velocity of the center of mass of the wheel about the fixed point O, which I'm referring to as the ground, in the k direction. And that's equal to 2 pi over t, because that's the like full revolution, and then the time it takes for one full revolution. And then that is equal to 1.309 radians per second. And then this is all around the I hat. So in order to get this into the k hat, this I hat is not perpendicular to k hat. So there's a component of this rotation that is in the k hat. And then so in order to find that, we can multiply by sine of 90 minus beta. And that's derived from this angle here. So this is 90 minus beta. And then so if you're trying to find I guess I'll try the pseudo triangle, like this component, which is along with the k hat, then you can do the sine of this angle, or multiply with the sine of this angle with the hypotenuse. And then so you get a value of 1.045 in the k hat radians per second. And then now you want to add up the angular velocities in the k hat direction, because you want to find the total w or omega k, and that is equal to 1.045 minus 1.64. So this is let's see, 1.045 minus 1.64 radians per second. And then I can write k hat. And then we plug this value into this angular momentum equation. And then we already derived this moment of inertia. So we multiply 175.78 by this value, which is in radians per second. And then you get HCZ equals negative 104.58 in the k hat direction, kilograms meters squared per second. And that's the answer. Thank you.
Okay, so I had question 2, which was trying to find the x component of the angular momentum for the body shown. So the formula we are given is the I of C, and this is double Z, equals negative the sum of the mass of each piece times x and the z component. So from here, I started with my
that's not ZZ, right? IXZ.
IXZ?
Yeah. It's the product of inertia.
IXZ. Okay. Yeah. So I had my thing drawn out like this. So x, z, and y, which is I hat, k hat, and j hat. And so with this in mind, I went and solved all of these, but since we're running short on time, I'll go a little faster. So for the first one, number 1, because it is in line with the z-axis, it's 0. So we're going to skip that one for now. So I'll start with the next one. So I move the negative to this side, so at the very end, I'll put the negative on. So we have xz, and for number 2, everything has a mass of 0.7 kilograms, and the length is 1.9 meters. So to find 2, I started with first the z-axis, and it's negative 1.9 meters in the z direction. And then I multiplied that by the x direction, which is positive 1.9 meters divided by 2 in the x direction. So that's our first one. The second one is number 3. So it's very similar. It's going to be the 0.7 kilograms.
So this is a scalar equation, so no k hats and I hats. Yeah.
No k hats.
We understand that it's x coordinate and z coordinate. Yeah.
Okay. So we have 0.7 kilograms, and then it's negative 1/2, and so it's going to be the negative 1.9 divided by 2. This is meters in the negative z direction, and then this is then multiplied by 1.9 meters in the x direction. So continuing, we see number 4 is also in line with x, so it'll be 0. Number 5 is also in line with x, so it'll also be 0. So then we move on to number 6, which would be 0.07 kilograms times, and that's first in the y or z direction, so that's 1.9 meters, now positive, divided by 2, times now negative 1.9 meters in the x direction. We then move on to number 6, which is 0.7 kilograms in the 1.9 meters, and this is in the positive z direction, and then we subtract. I think this is where it gets a little interesting. So for this one, we are going, I think I messed something up. This is number 7. So this is going to be negative 1.9 meters divided by 2 in the x direction. And then our last one is 8, which is in line with z, so it'll be 0. So this in total, if we move the negative to the other side, we get...
So whatever you have written so far is from the parallel axis theorem, right?
Yes.
And you've taken only the non-zero contributions.
Right.
But remember that the parallel axis theorem has another term. So because what you're getting is the moment of inertia or the product of inertia xz about the center of mass of the whole contraption, right? But you have to start with the same value of ixz about the ci for each one of them, right?
Each one.
So what about those terms?
So when you're saying about the CI of each one of them, you're saying the center of the bar from each one of them to the
right. So
center.
each has a center of mass, right? For
Right.
example, you've taken 2, so it has a moment of inertia about its center of mass.
Right.
Okay, it's a trick question. So
Okay. Because
but just think about it, because what you have done is you have taken that from the distances you have multiplied with the mass. That is just an additional term to the moment product of inertia about its own center, right? So what happened to that term?
So what I was thinking when I was looking at this, since we're eventually finding momentum, the way I was thinking of this was when you take the cross product of something. That's why I was canceling out the
you will get to
terms.
that, but even before you get to that,
Even before.
just to get to this
the uniform-
ixz, yeah.
Are you saying?
So this expression that we have, right?
Right.
So this is about the centers of masses of
Oh, because they're
I.
uniform.
yeah,
slender
but we are
rods.
taking about the center of mass of the whole thing, right?
Yes.
So why are we leaving out the products of inertia of each one of them?
Because each bar is uniform.
Uniform, so essentially it's a planes of symmetry that it has,
Right.
right? That's one thing. But even if planes of symmetry were not there, you have the thing that it is slender.
Slender.
The fact that it is slender means that it is almost like zero thickness. So ideally you're speaking. So essentially one of the coordinates x or z will go to 0.
Okay.
So because of which all those 4
Because
terms.
it's slender.
Otherwise you would have had not 4 terms but 8 terms.
Right.
Yeah.
Okay. Thank you. So then from here, I moved the negative to the other side, and because we're short on time, I'm just going to put the number I calculated, which was positive 5.054 kilograms meters. And so then from here, we take our next equation, which is HXC equals ICXZ. and then times the angular momentum, which is just a scalar, and the z. So to get this, we bring up our IXZ to this, which is 5.054, and bringing the units, and then we multiply that by the angular speed, which they give us as 6.0 radians per second. We have the 6.0 radians per second. So then this gives us 30.32 kilogram meters per second.
So here also there are two more terms in general equation for HXC. They will involve an omega x and an omega y as well.
Okay.
Right? So in this case, because all of your omega is about the z-axis, those two terms are going to zero. Otherwise, your IXX and IXY would have also contributed.
Okay, so then I also have the next one. So we are considering an aircraft with a velocity, and we are looking mainly in the roll direction for the momentum. So for this, we can do this. So this is in terms of the aircraft, but in the inertia frame of reference. So we have I for the frame of reference, and then we will be then using the equation. So we have IC as given, the matrix, and we're given that all of this can be computed out to match IXX. So each, when it's separated out into the matrix, it's separated out into the I terms and the I hat, J hat, and K hat. And so this is a way to then use this matrix to find the angular momentum. So we are looking for only the angular momentum in the roll direction. However, it's not just going to be the velocity in the roll direction. It's also going to have some velocity from pitch and yaw affecting the angular momentum in the roll direction. That's why we have to put it all out. So we get IC XY, IC XC, IC XY. And so I'm just writing out all of these so that in place of the numbers that we are given, to better write my equation before I plug in the numbers. And so I'll finish this here. And all right. And so we are trying to find the angular momentum in terms of 10 to the 6th. So I'm not going to distribute that until the very end. So from here, we want to find the angular momentum only in terms of this piece, this component. So when we look at this, it's going to be, I believe, this, or yes, is it this piece? Yes? Okay. So when we bring that down, our angular momentum, would it be a vector? Would it have a vector line? People? Friends?
Yes.
And then it would be, yes.
Is it a vector? Yes.
And then it would be A divided by I, for the reference frame, because aircraft in reference to the inertia.
Sounds right.
Okay, just that was the one thing I was unsure of. So A in reference to inertia, and then this then equals the I. It's dying on me. So we have the first one, which is the IXXC times P, and then we add that with IXYC times Q, and then we add that along with IXZC times R. And then this whole thing will bring down the...
So what you have is not the angular velocity but the angular momentum, right?
Yes.
Because PQR is what constitutes your omega.
Yes.
On the left hand side you have omega.
Yeah.
Yeah.
So,
That's just PQ and R along I, J and K.
along ij. Okay, so
Yeah.
this is
Once you multiply it by I,
Make it an H.
Yeah.
I use H.
h.
yes, because the angular momentum.
Okay. So like this.
Yeah.
Okay. And then do I also have
About C.
Yep.
So
H
superscript
and,
C.
to do I put the B1 hat, B2 hat, or B3 hat, or do I
No,
wait
no,
till
no.
the end?
No, this is just your B1 hat. The entire thing is B1 hat, right?
Okay.
So you will have B2 hat and B3 hat, but you don't have it in this particular problem, right?
Right. But I do put it with
Yeah,
here.
you don't need it for what you have to calculate.
So this is all of it. Make this go a little faster.
So you
This-
can just write H subscript X because you're taking only the X component of it. Let that AI be also there,
Okay.
and then you, yeah, because you're taking only one of those components, so it's no
So-
longer a vector. Yeah,
Because we're only in the X
Yeah.
components. Okay.
so it's no longer a vector. It's just the measure number along X.
Okay. So then we input the values, which since we're short on time, I'll actually just write what I got.
Just say it out loud. 'cause
That's
I'm
what-
also
that's-
at the same-
Yeah, go ahead. Yeah.
So it's pretty much the matrix that we have, which would be 1.1 times 10 to the power 6 times 0.15 plus 0 times 0.18, which would get cancelled off as you see there, and plus we have 0.2 times 10 to the power 6 according to the first layer times 0.19, which is the R. So if we get that, we get up to 203,000 kilograms meters per second.
But they
meters
actually,
squared per second, which
But
is
the-
equal to 0.203 times 10 to the power 6 kilograms meter second per square. We both
Yeah.
have the same questions, so it's
Okay.
repeated. So 2, 3, and 4, 5.
Okay,
the same
okay,
questions.
okay. But different things are asked.
No,
No.
same thing I asked.
are you sure?
This happened last semester as well. In the video, they just
Really?
the question. 'cause
Oh.
it's-
Okay.
Yeah. Yeah, the same questions.
Exact.
I realized that.
Same.
So.
And
Oh.
then, for example, we have the glorious Blue Angels doing a roll. And that's the real life.
It's much more exciting than the role I had in my presentation.
Yeah.
I mean, here we
Yeah.
just had to find for the roll.
Yeah.
We wanted to find for the other two. I also did that.
Okay.
So for the P, which is for the Q, which is the pitch,
Uh-huh.
we get 0.414 times 10 to the power 6 kilogram meters per second squared.
Okay.
I mean meters squared by second. Sorry.
Okay.
And then for the yaw, we
Mhm.
get 0.638 times 10 to the power 6 kilogram meters squared by second.
Okay. Good. While we are at it, it's another interesting thing that you could probably see here, because this is like a typical inertia matrix for most conventional shaped aircraft. So you will typically have a form like this. There are a couple of questions I'd like to ask you and see if you can intuitively think why it's so. Why do you think we have these 4 zeros? Any idea? And that's typical of pretty much every conventional
Because
aircraft.
we have one plane of symmetry.
Exactly,
down the-
exactly. And that plane of symmetry is which plane?
It would
Between
be
X, Y,
the
Z?
X, Z plane.
Yeah. So, which is why you see the Y coordinates are going to 0. The other thing which will also you'll see very commonly in most aircraft is the way in which this principal diagonal is. This is the lowest and this will be the highest and this will be in between. Can anybody say why this would be the lowest and this would be the highest?
Is it because most of the mass is close to the fuselage, which goes along the x-axis?
Exactly. So which is why this is lowest, right? So whereas here you're from the z-axis itself much more spread out. Yeah. Good.
From the operational point of view, there is one small addition. Can I say?
Yeah, please. Yeah.
There are two types of rolls. Roll itself can be two types. Can anyone tell me?
I think a barrel roll. if I
Absolutely. And the second one is?
remember. Oh, like aircraft roll?
Yes.
So-
Aircraft rolling can
Barrel
be.
roll?
So there's one barrel and then there's one on this spot.
And then this
Yeah.
roll.
Yeah.
See, what he is trying to do is a drum roll.
Drum
Yeah.
roll.
Barrel roll is you try to do on the same axis. You
Yeah.
just roll like this, like a screw.
So like Top Gun kind of a thing.
Yeah.
where they- yeah.
And drum roll is you do this.
Yeah.
There are two types of rolls.
That's useful, thank you.
So question 4 and 5, it's the same question.
Okay.
You want me to do it?
No,
we are short of time.
We can come back to this if we have time. Maybe
Okay.
we'll go to the different questions
because we have
first.
the same answers.
Let's
I
go
just
to
have done
the
some
more
stuff a
variety
little bit.
first, and if we have time, we can come to this. Yeah.
Okay, it's going to be a moment of inertia question. We're asked to find IZZQ in kilograms meters per meters squared. We'll start off drawing the coordinate system. X, Y, Z, K hat, I hat, J hat. Okay, so we're given 3 rods. We're told what their masses are and as well as their lengths. And so we know for the equation for finding the moment of inertia about its center of mass, we just sum up each part of the rigid body as well as add the parallel axis theorem part component. We consider like how far the individual parts center of mass is away from the overall center of mass. And so I think what we can start off with is first defining where each center of mass is for the individual bodies. So there's body, we'll say A for the bar along the x-axis, B along the y-axis, and C along the z-axis. So those are our three parts of the rigid body. And we know just because of the fact that it's a rod that it's going to be symmetrical.
Switched off and on.
The fact that our center of mass is going to be at half whatever its length is. So for example, for A, we're given the total length is about 1.2 meters. So that means for our A, our center of mass is going to be about 0.600. Same thing for B, we can do where B, the total length is about 2.3. 2.3. That means half of that length is going to be 0.115. And this is all in terms of meters. Same thing for C, we're given the length is about 3.2. That means that halfway to that point, or where the center of mass for C is going to be at 1.6 meters. So now we know where all the center of masses are, and so we can set up the equation that we're given here where we just sum up each individual component as well as consider the parallel axis theorem. So IZZ, and we're given about point Q. Point Q is at the end of bar A. So IZZ of Q is going to be the sum of, we'll do first for part A, we're going to consider the moment of inertia about its center of mass, which for a rod is going to be, I believe we have it on the board, 1/12 times the mass times length squared. It's going to be 1/12. Our mass we're given is going to be 1 kilograms for bar A, 1 kg. Our length we said before is about 1.2 meters, and that's squared. That's the first, this is the first portion where we're saying that's the moment of inertia about its center of mass. We also have to consider the overall distance from its overall from the center of mass. Okay, and then since we're considering this about point Q, we can figure out what that distance is. So the distance for A, its center of mass in comparison to Q is just going to be, I guess we can say it will be, there's a simplified way of doing it. Normally what you would do is you would have the center of mass it would usually ask for the center of mass about the entire rigid body, and that would be somewhere off axis, somewhere complicated. We're told it's on axis, and also we know that instead of doing d squared, like md squared, you can do x squared plus y squared about its center mass. And those give you like the same sort of results. And so if we do d, the distance a squared for this part A, we can see that it's going to be 0.6 minus 1.2 squared. That's basically the center of mass of A in comparison to Q, and this is only the x component, as we said, like the x squared here. And so we consider the y component, it's going to be 0, because both the bar A center of mass and the point Q have 0 as terms of the y coordinate. So this is going to give us a distance of about 0.36 meters. We can do the same thing for dB and dC. Squared. So for dB squared, B is not along the x-axis, so it's going to be 0 minus the coordinate of Q, so 1.2. It's 1.2, and the square goes outside. And that's our x squared. Our y squared will be the coordinate of B, which is going to be, as we said before, 1.15. Q doesn't have a y coordinate, so it's going to be 0 squared. And so that's going to give us a value of 2.76 meters. And now if we look at DC, we'll notice that it'll have the same thing where it doesn't have an x component because it's along the z-axis. So it'll be 0 minus 1.2 squared. And then we'll notice that in terms of having a y coordinate or being along a y component of its center of mass, z is along, or the center of mass for bar C is along the z-axis, so that's going to be 0. And then if we talk about point Q, it is also 0 because it's purely on the x-axis. So that ends up just being 0 here as well. So we get a value of about 1.44 meters. And so knowing that parallel axis theorem is just, we're adding mass times this distance squared, which we just calculated, we can do it here. So we do plus our mass. So for bar A, it's going to be 1 kilograms times our distance that we just calculated, dA. So it's going to be 0.36 meters squared. And then we can repeat this step for the other components. So plus, let's say 1/12. Our mass for bar B is given as 2 kilograms, 2 kg. Our length we said was about 2.3 meters. 2.3 meters squared plus our mass again, so 2 kg, times our distance, so 2.76 meters. And then notice there's no, there shouldn't be a squared here because we already considered the squared when we plugged in the equation, so that should be fixed. Okay, and plus the last component, which is going to be 1/12. Our mass here, I believe, is 3 kilograms. 3 kilograms. Length is about 3.2 meters, and that is squared. Plus our mass again, so 3 kilograms times our distance that we calculated of 1.44 meters.
Those are all in meters squared.
These are all in meters squared? Oh, these are meters squared, yeah. The ones that I calculated as d squared are just already squared. That ones were good. This one. This one. Meters squared. Yes, yeah, I should have put it, no, that's right. Okay. I think the units work out. And so if you add this all together, we get the final answer of IZZ about point Q is equal to 11.21, and we'll get the units of kilograms meters squared, because each term is multiplied kilograms times meter squared, kilograms meter squared. So that's your final answer.
Let's move on to the last question.
Just skip to the last?
Top. And then if we have time, we'll come to the others.
I think we wanted to do this one together.
Good, yeah, that's great, yeah.
Any?
Very good memory.
Let me get water. Shower and then figure out what's also process.
You'd like to start? Would you like someone else to start?
Let's just do it together.
Alright.
Okay, we're given this top.
so we're given a top and we're given.
Here's the microphone, right?
Oh yeah, I have it. Yeah. It's just passed around.
Cool. Yeah, we'll pass it around. We're given a top and we're given its angular velocity in terms of the angular speed around the z-hat direction, which is in the inertial Earth fixed reference frame. So that's one piece of information we know. We also know the geometry of the top, which we're treating as a cone, and we're looking to find the rate of spin psi dot around its axis of symmetry, around the z, which is in the reference frame that is oriented with the axis. The z-axis is the axis of symmetry of the top. We're also given the angle alpha, which is the angle between these two different z-axes in our two different frames of reference. And so some important pieces of information here is we know that gravity is acting on the top, and so we know that we can find the moment and where it acts. So we can find the process for this question, as sort of explained by the hints in the bottom, is that we need to relate the angular velocity of the top in an intermediate reference frame to the moment that is acting on the top due to gravity, because that depends on the angle alpha. So first, I guess we have our diagram here as shown. We're going to need to define some reference frames and coordinate axes.
Yeah, you can take over the next one.
Okay. Someone else wanted to take the mic. Got it.
So we're first defining the intermediate reference frame.
Should we specify the? We didn't write all the axes for the Earth fixed one.
Probably should. And then likewise, there's just another pair of axes for the.
Here, maybe do a different color for those. So
That's a good idea.
this is the new. Is this the new reference frame right here? In terms of rulers. So like some of them.
This was
That.
This was the equation activities. Is
Okay,
that
yeah, that's exactly
pretty
what I was
similar?
thinking of.
Okay. And then,
I keep holding it.
cool. We got the. Sorry, that's sideways. Let's call the intermediate the intermediate reference frame. I guess the way that's written in my formula is as G, and let's call the body of the top as T. So the easiest thing to do here is to choose our point for the purposes of this. Let me finish writing this.
Would you pick the point at the on the top of the top? Like
You could. I was thinking that we could use the point that's the center of mass because
right, that yeah.
it's known. It's a known quantity for a cone. Is that what you were trying to say, or?
Yeah, I think that's what I meant. Yeah. But there's and of the intermediate frame. I think I keep thinking top means like the top of the top, and I think I keep reading it wrong.
Yeah.
Okay. So when we look at this formula, this is our moment, which we can find using gravity. We can also, another important thing we can define is the moment of inertia of the cone. We already talked about that. And we can find the angular velocity. I believe this is of the top with respect to the inertial reference frame, and then we're going to define that in terms of the intermediate reference frame G as far as the coordinate axis is concerned. We also have this term here, which is the moment of inertia times the rate of change of the omega in G. But because we're told that it is steadily precessing, I believe that this term, since like it's a rate of change term, is just going to end up being 0. So that simplifies our process a little bit. Does somebody want to talk about the moments of inertia?
So before we get to that, can you be a little more precise in that equation? They're all vector quantities, right? M, omega. And for all the omegas, the other two omegas are fine, but the first omega you have to say omega of what with respect to what?
Okay, so it's the top with respect to the inertial reference frame, I.
Okay.
So, for the moments of inertia, is that what you want?
Right, or
Here, I can.
just to make it more.
For the moments of inertia, so we're trying to find the moment that is induced by the gravity, and for a cone like this that is it's steadily precessing, it doesn't quite say uniform, so we don't know if it's the complete density, but if it was a uniform cone, we could then assume that the center of mass was 3/4 up the center towards the apex, so that would be roughly in our drawing this 3/4 on this line through the center of the cone. So there we would take that in terms of the 3 axes and then take the cross product of that with gravity to find the moment of the cone in relation to gravity. Anybody have anything to add?
Sure. I guess then the challenge with that is that we know that gravity is pointing in the negative z hat direction in the inertial reference frame with the Earth fixed coordinate system. But I believe for this expression, we're trying to find everything in terms of our intermediate reference frame G. So we're going to need to use the angle alpha and our coordinate system to change the, to put it into appropriate direction vector form.
So we have to find the moment that gravity creates in the intermediate reference frame.
Okay, so if we look at the geometry, let's see.
Could we change this to like a dot, because we're going to take the cross product eventually and we don't want to confuse it. Okay.
The gravity is acting in the negative z hat direction in the Earth fixed reference frame, and it's at an angle alpha. So we know that some of the component of gravity. I think the way that these axes are drawn is maybe a little confusing.
Yeah.
I think it should be more like that.
Yeah. Is that X?
This is Y. X is not here. This is the way that I did it.
Okay,
I
wait,
think
then
that's
what's
right.
that?
These should be all prime, right? Because it's a different coordinate. This is the Earth.
Oh wait, then what's this? This is the intermediate, okay.
Yeah. So
this is G.
we know there's a component of the gravity force that's going in the z-hat direction. It's pushing the top down towards its point, and then one that's pushing it in the y prime direction, which is towards the ground that way. And they're related by alpha. So I believe we can write.
I have it being the.
It's the mass.
So I have.
Mass times gravity. And you have it as.
To solve for the moment. That.
Oh, for the moment.
Yeah.
For the moment, we only care about the component that's in the y prime direction. I believe
Yeah.
that's right, because otherwise it's just pressing along the axis that we're trying to find the moment about. So the y prime direction should be the sine. That's what you said, right? Sine of alpha. And then we know that Gracie, you said that we know that gravity's going to act at the center of mass, which is 3/4.
3/4 of the height in the center of the
Say h of the cone. So this is our moment, and we know all of these quantities except the mass, but the mass,
Because it's going to be 1 kilogram in this case.
right.
And it says that it will also cancel on the other side, right?
Okay. So then we'll worry about that later. We can leave it in for now. So next we have to define, we have 2 things left. We have the moment of inertia of the top, and then we have the angular velocity of the top with respect to the Earth in the G coordinate system. Does anybody have ideas for how we want to approach this?
You have to find these 3 quantities, right?
Yes, and I think there's 2, right? Because those 2 omegas are the same.
Okay.
Can you just go off like what we know? Like we're given the RPM. Do we know what that is?
Aren't we trying to find the RPM?
Or we're given RPM. Or we're given the
Oh, the omega around
yeah. Like what kind of angular velocity are we considering that as? Like what is it with respect to?
Well,
So-
67 RPM times 2 pi would be radians per minute, and we can divide by 60 per second.
Yeah.
I think the challenge here is we want to find omega in the coordinate system that's like aligned with the top,
Yeah.
which is at an angle to the axis that it's rotating around the Earth,
Which is angle alpha.
which is angle alpha. So if we say
So we could do the same frame of reference transformation that I did in my earlier problem with the
Okay.
matrices.
So we're basically
Matrices,
using
yeah.
the moment we find about the cone axis and relating it through with alpha to find the mid.
yeah, alpha, which tells us alpha and omega, like capital omega and alpha will tell us little omega.
Okay, so would the transformation matrix be so we're only changing
Do you have the microphone with you?
Yeah, no, so we're changing the axis, right? So it'd be
We're changing all the axes
oh right, okay.
because they're all orthogonal to each other.
Okay. But we don't have another angle other than alpha.
I think. Yeah, but they're all related in terms of alpha.
Oh, it's that.
Okay.
I'm not sure how your transformation matrix is set up, but we may not need the entire
Yeah, that's
transformation matrix because we only have one.
Yeah, we only need to do it in terms of speed, I think. So-
Gracie, can you pull up the moments of inertia formulas for a cone?
Yeah.
We might need that.
Oh wait, that's an equal to. Yeah. So that would be the transformation matrix for just the z coordinate.
Okay, and then we know we can define the omega in the inertial, the I reference frame, and then we multiply that by the matrix to find the omega in our intermediate reference frame. Is that correct?
Yes.
So the vector form of the omega in the inertial reference frame is just capital omega k hat.
Mm-hmm. So times right?
Mm-hmm.
So first we have to figure out the values for that, and then we can go from
Well,
there. Right?
if you multiply that matrix out, it seems to me like it's going to give you the same thing. Are we sure that's the correct translation matrix? Because it's gonna provide the same thing. Maybe we should think through this conceptually. So
Wait, how would it be the same thing? It would be cosine alpha times omega
But
And then
when you multiply, isn't it like that? I'm trying to remember from my linear algebra. Yeah. No, that makes sense to me. While Lalita, do you want to double check that while, and then we
Yeah.
can, like Gracie, we can find the moments of inertia of
Sure.
the cone that are relevant.
All right. So I got one,
Maybe
two.
on mic.
So I pulled up the momentum of inertia for a cone. And
Do you want to write?
I can write which. So for it starts with just I'm gonna put it up here. So I'm gonna write small. It starts with the moment of inertia formula starting off like this, which I believe what they're trying to say with this is the element is about an axis. So with it having the change in the inertia, change in mass, times the radius squared over 2.
I don't get why that one.
So from here they plugged in all the different pieces of it, which they used pi x squared for the area of the cone at one point times 10 alpha dx, and they were using this to simplify it in terms of one singular axis and a radius. So with the derivations from this unit, or this, they bring it all the way down to I of a cone
Yeah, that's what I did.
is equivalent to 3 times m, which is, I believe, the,
I got it.
The mass.
I want to say it's the mass of the cone, and then, because we're talking about the change in mass here,
That's right.
and then we have r squared, which is the radius at the bottom, so it would be where the radius of the cone around in the circle,
You
so,
know that.
yeah. And then we have all of this divided by 10,
Okay.
which,
And that looks like it's the moment of inertia around the axis of symmetry.
yes.
So we're gonna try to find the entire inertia matrix for our multiplication, but we can take advantage of the fact that the cone has 2 planes of symmetry and say that all of the products of inertia are 0. And then we also know, because of that axial symmetry, that our moments of inertia about the x and y axis should be the same. So we have the moments of inertia about the z. Now we need to find the perpendicular moment. I think I have a formula
You might
here.
have, yeah, so the perpendicular moment, I'll write it right up here, or probably,
Is 3 over 80 times the mass of the cone, and then in parentheses the height of the cone squared plus 4 radius squared.
alright. So I'll move that far away. And that is the perpendicular.
And then we can write that in our inertia matrix form. These are all formulas for the moments of inertia about the center of mass.
Inertia matrix one, which is. Did you recommend?
Okay.
What is the form for an inertia matrix? Is it XX, YY, Z? Yeah, the products.
Yeah.
Should someone hand the mic to Lalita? Or
I have for both.
what's going on?
Alrighty. So, quick fix. So the simple rotation transformation matrix from A to B by one angle is this. So I just put the stuff in the wrong place. So if we multiplied this out, then it would be omega times sine alpha plus cosine alpha. So we can write that here. The result will be
You write those frames A and B in terms of I, E, and J. That's what
So
this problem.
Yeah. So this would be IE to GE, right?
Well, hold
I think
on.
it
What
would
is
be
it?
G.
one as T as well, right?
So the T is the top, the body. G is our reference frame that we're
Trying to go
trying to
to.
go to, and I is the inertial reference frame we came from.
So we're going. Oh no, this.
I think that
That's okay. We also need to put unit vectors in this expression. So I believe this should be our second unit vector, which is y prime hat, or
For the whole
j
thing.
prime hat, I guess. No, because each component, right? When you
Okay.
wait a minute. Yeah.
And then this would be K prime hat.
Yes.
Cool.
So that's what we need, and this is our expression for this term, correct?
Yes.
So now we know this term, we know this term, and we know this term as well. Should we try to create some more space on the whiteboard before we finish the solution? I'm not sure. I don't want to erase too much information.
You can erase the top part.
And the rotations. Yeah, you can erase the rotation. That's
Where?
fine.
can erase the phones too.
The rotation
the-
matrix that we just used, the sine cosine one,
Yeah,
Oh,
yeah.
that's okay.
because we have the following results.
And then you can erase the top right hand.
The drawing?
The DI, DM, top right.
Yeah, that's okay.
Oh. Okay. What else do we need here? We need this. Oh yeah.
Cool. Okay, so we have our left-hand side. Someone want to write the right-hand side? I can do it too.
That's fine.
So we have our.
We have that, and we have I. Do you want me to write out?
One thing that we can do to simplify things is take out some of the constants from our inertia matrix and from our moment term on the left. As we can see, they both have a mass in common, which again checks out with the hint and our assumption that the mass cancels out. So we can cancel out the mass on both sides. We can also cancel out the 3 on both sides.
Sorry,
Doesn't matter.
we're rewriting this equation, right?
Yeah. Simplify things a little bit. But now we have all the pieces that we need to find the solution.
So this is just 2 times that. And where's the math again?
Right,
Where's it
okay.
cancel?
This mask
And then in the green matrix as well,
Mm-hmm.
Right, okay.
as well as the 3 will cancel.
Three's on the top. So 3. You see the order?
Right.
So 3. Cancel the mass. Cancel. And then we can write it in terms of HG sin alpha.
Okay, so moving forward to that side.
You can either keep the 4 here or move it, whatever you want. 1 over, because this would be 120.
You can see
Yeah.
it in the
1 over 20. 1 over 20.
should be 80.
We brought the 40
Okay.
away. Is that R or
I think it's a. Oh, it's a.
It should be an R.
It's R. Times 4, right? The, is it 4?
We canceled it out with the
Yeah.
80s.
Yeah.
We
Oh,
divided
The 4.
the
Divided
bottom
by
one,
4.
yeah. So that's 40.
Is it not being multiplied by 4?
Yes.
Should be multiplied by 4, yeah.
4 r
Well,
squared
this is
over
divided by
10.
4 and this is divided by 80. So if we multiply by 4 and multiply by 4, it gives 20.
Yeah.
So we have to multiply by 4 here. So it's
Yeah,
4
listen
r
if it-
squared over 10, which is 2 r squared over 5.
Okay.
Okay. Now what?
So
We know the entire left side, right?
We
We
can.
do.
Know the entire left side. Do we also know the entire right side? I
We-
think
we know radius of the cone.
yes. So
What is big R? What are we considering that?
It's radius.
it's the radius of the cone. So I think we have a missing piece here as far as where psi dot gets integrated into the rate of spin, because psi dot is related to the maybe we missed something when we calculated the omega, or when we used the omega to calculate that. I think the part that we missed was that we said that the rotation of the top came only from the rotation about the Earth's z-axis. It also has the psi dot, which is what we're looking to find, right? So I think in our omega expression, we also need to add a psi dot times k prime hat.
To this one?
Yes.
Right.
So we added.
Yes. And that's our unknown that we're trying to solve for.
Plus.
Psi dot times.
K hat.
K hat.
K prime hat.
Okay, and then omega we have.
Oh,
we
also,
have-
I guess an important clerical thing. On the left, we need a vector quantity. I believe the moment that we calculated,
Here.
the moment was about,
About the Z prime.
well, isn't gravity acting, it's not spinning the top.
Yeah.
It would be the,
Or z prime with an angle.
is it the x prime?
Well, this would be in the intermediate reference frame because
Yes,
that's
yes.
also in G.
I'm not, I think if you look at the reference frame for the top, gravity's gonna tend to pivot, make alpha larger.
Yeah.
So it would be about the x prime. The moment would be at the x prime hat.
That was right.
Yes, I think so.
Okay.
So we're saying it's pushing it. And then, okay.
We're saying it's pulling it towards the ground.
Right.
All right. So we should let's move the
So this is equal to omega.
we have the inertia matrix there.
Okay.
We need to write the cross product. Like, you see how we're missing.
Cross between
This.
the
The.
angular velocity and
Right.
Yeah, I also think this. I'm not sure what happened there.
Oh, because we canceled out inertia here,
Mhm.
but then we still have that there, right? So if it's +2, then that would simplify to that? Or is that not right?
I think because there's a cross product, that doesn't necessarily work.
Okay.
So we need to multiply omega by, or the matrix I by omega. So can we do that on the board? Maybe we can erase the green.
Okay.
And then we have our omega vector, which we just found.
Okay, so we're
Okay, so
multiplying
omega.
this by omega?
It's the expression that you have below in blue
That's what you're multiplying it
Okay.
as
by.
vector.
The whole thing.
So the first component of the vector is 0, and then you have a,
Don't forget the omega with that sign.
yeah, you need the
The omegas.
psi in the third term and the omega,
Oh, right.
big omega,
Sorry,
and then add,
And then the top one is psi, right?
Isn't I thought it was the
think
bottom
it's the
one, right?
bottom.
Because that's
Well,
about the
this
top
also,
spin spot.
This is
Right,
also
you-
so it's
So it's
added.
added, yeah. Okay, very good. So then when we multiply that out, I believe
X will be 0, yeah?
the
So the x prime hat.
x prime hat component is 0, so we don't need to write that. The y prime hat component, you want to take that?
It'll be the omega sine alpha divided by 20 times h squared plus 4r squared.
Times 20
And then,
divided by
Multiple divide by 20
oh, okay.
yeah, so it's omega sine squared
times
divided by 20.
h squared plus 4 squared plus 4r squared.
And then in the z prime hat direction, someone want to take that?
It's gonna be 2r squared over 5 times the last component. Yeah.
Okay.
So this will be your yeah.
Yeah.
Might as well just write 0 in I hat direction. Okay.
Doesn't this not match up if we compare it to the left side?
So it doesn't. But that might not necessarily be wrong. It could be that we identified the wrong direction for our moment based on how the coordinate system is drawn. But it could also just mean that we have 3 components, and because there's only one measure number for each component,
It would be the magnitude.
well, we know that the magnitude, like if we moved all of our terms to one side and set them equal to 0, we
Yeah.
have one term on the left for each component, and then we know that each of those components would have to be 0. But
And we have all the variables here. Can we not
So that would
get
mean-
inside?
yeah, we have to get it in terms of a scalar equation.
Let's see.
So we could
The
say
scalar would be the magnitude, no? Of the
yeah,
vector?
but we need to figure out what the magnitude is. So if we say that
7.01.
the
Yeah, so
k hat component
times 2 pi by 60.
so the k hat component is
Times
given
2 pi
there,
by 60. No.
Right.
and if we say that that component has to be 0 because there's no other
That's how many
k hat
Yeah.
components in this
Yeah.
equation, then psi dot would be equal to negative omega cosine alpha.
Yeah.
If you plug that into the calculator, does that get us our answer?
What?
Are we?
What is negative omega cosine alpha?
Negative omega cosine alpha. Cosine alpha. Alpha we're given in radians.
Yes.
Degrees.
Oh, degrees.
I got negative 50.
Okay, so that is not right.
If I multiply out that 2r over 5, I get 33. And then for that first term, I'm getting 285.
So
And what? 285.
like if you plug in all the
It
numbers,
should be
for that-
222. If you take the magnitude of all those numbers, what do you get?
well, you have the psi, which you don't know. So you can't do that.
Yeah.
So let's see. I think we made a mistake somewhere. On the left side, are we sure that our gravity moment is about x prime hat?
It's only negative, so that's positive. So
Maybe.
I think that has to be around x prime hat.
That does make sense.
I'm not sure what else it would be around.
What about our transformation matrix?
Do you think that was wrong?
Potentially.
I think it might have been.
Guys,
Mhm.
getting late for the
Oh.
meeting there. So can we Is it possible for you guys to make a virtual presentation tomorrow, or whatever's the remaining?
Yeah, we
Just this.
Can,
Could we do?
Yeah.
Could we do a Zoom of all of us zooming in together? Because we have a final tomorrow in jet propulsion.
Okay.
yeah, the finals at
And then
That's in the evening, right?
Yes.
No.
it's
No.
at noon.
It's at noon.
It's at noon.
it's at noon, and then we're all leaving, or a lot of us are leaving
Yeah.
pretty soon after that.
We could do a Zoom meeting.
Next week.
I don't know about next.
can we not do it tomorrow? Or we have time.
I mean, I'd be willing to do
Potentially.
it like just after the final, a quick Zoom meeting.
That'd be like 5.
Yeah.
I would be here at that point, so
Hmm. Yeah.
Alternatively, if you want to simplify it, we can all make like videos and send
That
it
would
to
be
you
better.
each
Even
problem.
better. Yeah, yeah. So you can work at your own times of convenience from wherever you are.
Or we just all
so all doing the problem
Yeah.
by ourselves.
all this problem, or are we doing each our individual? Because we skipped a bunch.
Yeah, I mean, if you have the solutions for the remaining, you can send that by video as well. That will be better because all of them I have planned weightage for, so
Right.
it would be good if you have the solutions to send them as well. All of them by video.
So just send the solutions of the ones that we haven't done, and
Yeah,
then
yeah,
as a
exactly.
group, I think we should do this problem.
True.
Okay.
So nobody erase that.
Yeah, we should take a picture of the board.
Yeah.
That we were at this point.
This was the
Also,
problem
if
that
you
was
all
just
up